Yes, hi guys. Today I'm talking about now area of surfaces of revolution. We have discussed up to the last lecture series that volume of solids of revolution. Okay, now volume that was the volume of solids of revolution. Now we are talking about area of surfaces of solids of revolution. Okay, whatever the solids which are revolved around the line, okay, axis or around the line, and then the solid is generated, we have to find out area of that solid now. So areas of surface, okay, of revolution, area of surface of revolution. This is the topic today. Area of surfaces of revolution. Area of surface of revolution. Now today I am taking for Cartesian equations. After that for parametric, then polar equations. But today I am talking the definitions of every part of this. I mean, what is the formula for Cartesian equations, what the formula for parametric equations, what the formula for polar equations, everything I'll talk about. Okay, and now area of surfaces of revolution. So what is the definition of this that I'll discuss about, and after that I'll take these 13 questions. I've taken 13 questions. All these 13 questions are based on the same topic, okay, for Cartesian equations. In this case, area of surfaces of revolution. Okay, area of surfaces of solids of revolution or surfaces of revolution. No problem. Now let me define that. What is the, how to find out this? What is the definition of this? What is the formula for all these Cartesian equations, parametric equations, Cartesian equations, sorry, polar equations, as well as when the surfaces revolve around any line other than the axis, then what is the formula? So that also I will talk about. And okay, so let me take the definition part of this. If definition here, let me take y equal to fx be a continuous function. Let me take be a continuous function, be a continuous function of x. In this case, fx. So it is a continuous function of x. Okay, in the interval, in the open interval, or in the open interval. Let me take, or in the interval. This is the open interval AB, let me take. Then the area of the solid, generated by revolving the arc, any arc. Let me take, in this case let me take AP arc, any arc revolving the arc measured from a fixed point, to another fixed point, to another point. Let me take P here, x by, and here from a fixed point A, let me take from a fixed point A to another point P, x by, on the curve between the ordinates, let me take x equal to A to x equal to B, is given by the area of surfaces, then the area of the solid generated by, or the surface of the solid generated by revolving the arc measured from a fixed point A to another point P, okay, on the curve between the ordinates x equal to A, x equal to B, is given by sine of integration. This is twice pi. Let me take here twice pi. Here it is y into ds. Okay, between limits A to B. Here x equal to A to x equal to B limits. This is the integral sign, or can be written as twice pi sine of integration A to B. This is y into ds, where S is the length of the arc is the length of the arc. This in ds, s is length of the arc. AP I have taken here, arc AP in this case. S is length of the arc AP. Okay, this is the formula which is for by ds when the curve is revolved. Okay, and the point generated by revolving the arc measured from a fixed point A to another point P about the line axis of x. Okay, this is about the axis of x also. We have to write here on the curve between the ordinates, this and this, about, let me write here, about the axis, x-axis, about the x-axis, in this case the x-axis. This is revolve about the x-axis, then this is y into ds, 2 pi into pi. If it is about the y-axis, then it will be x into ds. So let me now prove that what is the value of this, how this formula is obtained. So let me take an arc. Okay, here is an arc, let me take. This is AP arc, or if I take a point here A, and this is P point, this is Q point, let me take, and here it is AB point, this is B point here. Okay, here the ordinate is x equal to A. Here the ordinate is x equal to B. So this is x equal to B. This height is, and this is x equal to, not height, but this point is x equal to A here. At this point, x equal to x coordinate is A here. Here it is B point. And if I draw perpendicular from P to the x-axis, this is x-axis here, this is origin O, this is y dash axis, this is x dash and x O origin. Okay, now let me take these points as, this is P and Q. I have taken elementary strip here, where P and Q are two neighboring points here, P and Q. Coordinates of P are x and y. Let me take, this is x and y, and here coordinates of y or Q are x plus delta x and y plus delta y. Here the coordinates of Q here. Okay, now let us discuss about this. If I draw perpendicular from P to the line this Q, if I take here RS, let me take here R, this is S here, this is P, and this, let me take M point here, and if I take P so that it is clear, let me take P here, and if I draw from Q a perpendicular which meets PS at point N, let me take here. Okay, this is the perpendicular. Now this PQ is the ds length, smaller ds, and from A to P length is S. S plus delta S is the length of AQ, and AP is S, and AQ is S plus delta S. Okay, or ds. Let me write here that P x by and Q x plus delta x and y plus delta y B or R are two neighboring points, are two neighboring points on the curve y equal to fx. Here this curve is y equal to fx. This is y equal to fx curve. Okay, so I have taken these 2 points here. Okay, y equal to fx, these two neighboring points, and so P as be dropped perpendicular. Okay, drawing perpendicular or drawing PS and Q are perpendiculars from or perpendiculars on x-axis from P and Q on the x-axis. On the x-axis, we have got the perpendiculars. Then PM is perpendicular to QR, and PM is perpendicular. This is perpendicular symbol for perpendicular. Okay, reverse T or inverse T here. So this is perpendicular symbol. PM is perpendicular to QR, and QN is perpendicular to PS, extended PS extended. Got the point? So, and this length PQ, QN and PM are practically equal. Let me just check. The length or the arc length, the length PQ, QN and PM are practically same. Are practically same length, equal or same length, are equal, practically equal. Okay, this length PM, PQ and QN, we have taken equal lengths. Now let me take areas. What is the area of, or let me take the length of this AP that we have already taken here. Let me just describe here now. Let me prove this, that this area is, how this area is equal to 2 pi y into ds and limits a to b. So that I am discussing here. Okay, now let area of the curve A, and here I have to take some point. Let me take K here. This is AK point, and this B AK. Let me take L here. Okay, so AK and BL. So this is the area I am taking here. AK. Let the area of the surface, area of the surface AKSP is capital A. Let me take, and that of AKRQ, AKRQ, this whole area is A plus DS. Let me take, or I'm sorry, A plus DA. This is a minute bigger. So this area, so area of this one, which one, this area under the curve, this one is A, sorry, this NPSR, so PSRM, let me take, so is A plus delta A. Therefore, area of the elementary strip, what is that? PQ RS is equal to DA. This is A plus DA minus A, that means DA. This is the area of this. So this DA is the area of this. Now this area we have to calculate of this elementary strip. Now since this area of this, this length ds equivalent to PM or NQ, so this area is, let me take, so area of this PMSR or N, okay, and this, what is the area of this then? Let me just find out. This is this is by height, and this is by plus delta y. This is this height. Okay, so dA upon ds. So what is the area of this? Now this length is ds here. If I, or PM is also ds. This is also ds. Here PM is equal to PQ is equal to QN. We have taken here ds, the smaller arc length PQ is ds here. Therefore, DA is lying between this. DA is lying between. So DA is lying between this whole area is lying between. Let me write what is the area? This by into ds. Okay, this is by into ds, or let me just multiply this. This is by into ds. Okay, this area is. But if I find out the circumference of this, okay, so area of that will be. Okay, let me just find out that area. That will be equal to dA is smaller than, or dA is lying between, with that 2 pi into by into ds. This is area of by into ds. 2 pi into by r is circumference of this whole. So this total area of by into ds. This is area of this value, because this is circular length people take. If this is revolved around x-axis, so dA is lying between. Let me first write this. The dA, this area is lying between area of PMRS revolving around the axis. All these are revolved around the axis. Okay, so area of PMRS, okay, PQ, and this area is PQRS, but this area is a smaller one, and the bigger one is QN. Let me take NQRS. So these two areas, okay, which is area of the surface revolved around x-axis, after revolving x-axis about x-axis. So area of PMR and NQRS, area of this and this. That means this 2 pi by ds is smaller. Let me take this is dA is smaller than, this is 2 pi into by plus delta by into ds. Why this is? Well, this is the area of the surface revolved around the x-axis. So this 2 pi r, we know that with this dA. Therefore, dA upon ds is lying between, or this 2 pi is smaller than dA upon ds is smaller than 2 pi by plus delta by. Okay, so when delta x tends to 0, or you may say at delta s tends to 0, here it is delta s here. When delta by tends to 0 and delta x tends to 0, why? For this dx, this is length dx here. Up to this is x, this is dx. When dx tends to 0, here it is dx, this is dx length, x plus dx. Okay, so when dx tends to 0, let me take here. At dx tends to 0, delta by or d by, this is delta by here. If delta x tends to, let me take this is delta x. Delta x tends to 0, then delta y also tends to 0. Y also tends to 0. Then also delta y tends to 0 also. Okay. In that situation, this is there. It means dA is equal to 2 pi by into ds only. So this is lying in between these two. That means this dA is equal to ds into 2 pi by delta by 0. 2 pi by, this is also 2 pi by, this is lying between this. So dA is this. This is the area of this. Now if I extend this from this AK to this one, and if the x, okay, x is limited from this point to this point, this is x tend to, or here it is x equal to a to b if I put the limits. Therefore, area of the whole surface okay, by revolving this arc AB between surface between the ordinates x equal to A and x equal to B is given by, this is sign of integration dA limits A to B is equal to, here A to B limits, this is equal to 2 pi sign of integration by into ds, this is A to B. Okay, therefore this dA is nothing but area A. Integration of this will be A, dA is A, or 2 pi by sign of integration by into ds, A to B, here x equal to A to B is equal to area A, this is A to B, that means area of the surface, okay, under the curve is y equal to fx, area of the surface at x equal to B minus area of the surface at x equal to A. But at x equal to A, when x is A here, if I put here, it means this BL will coincide with AK. That means this will tend to 0. This means it is equal to A only. Therefore, area A is A here, or whatever the area here. Area A is equal to this. This is the area we will take. Okay, let me take this is equal to A. So this area A is given by this formula. Now let me talk about second condition. So this is the formula for finding the area of the surfaces around the x-axis in this case. Okay, if the function y equal to fx, okay, is continuous and area under the curve and area under the curve y equal to fx and the curve y equal to fx is revolved about y-axis. In this case, in first case it was in about x-axis, now it is about y-axis. Then area will be what? Then area is equal to 2 pi sin of integration. Let me take here y is equal to A, y equal to B. Again limits are A to B. I am taking A to B or C to D, doesn't matter. Limits are, we have to find out limits. In this case it will be x into ds. Okay, here limits are for y, x is replaced by and then ds upon dy we have to find out. So in this way we will calculate the values. This is the second formula for Cartesian equation. That was the first formula, 2 pi by into ds. That was the first formula. Second is this 2 pi into x into ds, limits A to B. Okay, this is for Cartesian form. And Cartesian equations are given, which is the topic of today that are discussed. But if the equations are given in polar form, then what we do? Now here ds is calculated. Let me talk about ds also. Here ds upon dx is calculated like this: 1 plus this is dy upon dx whole square. Therefore the area will be given by 2 pi sin of integration A to B. We will write here y into ds. This was ds only, ds upon dx into dx. This ds upon dx, this value will be substituted here. Okay. Similarly, in the second case, if it is d by here, ds upon dy we will calculate. That will be 1 plus dy upon, so dx upon dy in that situation. That is the point. Okay, so this is the formula here in case of Cartesian equations. But in case of, let me take parametric equations here. If the function, okay, if the equations are given in parametric form, second case. This was for Cartesian equations we have discussed about, which is topic of today. Okay, let me discuss about parametric form also. Because parametric form we will take the next lecture series. Then I'll take polar form. Instead of discussing, okay, at that time I'll discuss about all these 2 points. But this topic is very current here. So let me discuss about other forms also. There are 4 types: Cartesian form, first, then second parametric form, polar form, and there is 4th case when the area is or the surface is revolve around any other axis, any other line other than the axis. That is the 4th case. So that 4th case let me discuss about also, so that the topic will be clear for other lecture series also. Okay, and at that time I will remind all these things, but let me discuss that also. If the function is given in the parametric form, the function is given in the parametric form, then let y equal to, we are given here ft, and x equal to, let me take gt. Then what the formula here? Then dy upon or ds upon dt, in this case we have to find out. You will find out here dy upon dt, dx upon dt, that we will calculate from here. Then we have to find out dy upon dt and dx upon dt also. But ds upon dt in this case is given by square root of, this is dy upon dt whole square plus dx upon dt whole square. This value ds upon dt we will calculate. And what is the formula for that? So area of the surface of revolution, in this case will be given by revolution is given by A area is equal to 2 pi. In case of y here, let me write a Cartesian form first. This is A to B, we were taking the limits here, and it was pi into ds. Okay, but this is converted into 2 pi. Here limits are t equal to t1 to, let me take t2, t equal to, now we have converted this into t. Y is here ft, this is f into t. Now this ds is ds upon dt, we will write it as ds upon dt into dt. So ds upon dt is replaced by this. First, let me take second equation. Third, this is the first one, this is second one, and this is third one. From third, we will write here the value of ds upon dt. This is the value here. Then we will integrate this with respect to t. Limits are now in terms of t. So t equal to t1 to t2. This is what the formula for parametric form. Okay, this is your second important topic that we will discuss in the next lecture series. Okay, and in case if it is given polar form, let me talk about polar form also. What is the formula for polar equations? If the function is given, this is the third case, is given in polar form, let r equal to f theta here is a function, is a polar equation. Then what we do? We find out ds upon d theta. Sorry, ds upon d theta we find out, which is given by r square plus dr upon d theta whole square. This we calculate here, r square plus dr upon d theta. whole square, and this value of ds upon d theta. Give the formula. Then area of surface of revolution in this case is given by a is equal to, again 2 pi. We will write here limits here a to b. Let me first write the basic formula for this is y into d by. Now this we have to replace by here is given by, this is by the value of y in polar form. X we always write r cos theta, and y is r sin theta in polar form. We replace, so this is 2 pi. Now limits here theta is equal to theta 1 to theta 2. Let me take theta 2. Limits now in theta. Theta equal to theta 1 to theta 2. Let me take y is here r sin theta, and this ds is written as ds upon d theta. Now ds d theta is this equation. This is second equation. This is the first one. Okay, this formula is this one. You will integrate this with respect to theta. You will replace r also. Whatever value of r is given in the function given, this equation is then solved. So this is your third important formula, which we will discuss about in next third lecture series. That means this is 97, 98, 99. 99th we will discuss about polar equations or polar form in case of area of surfaces of revolution. Okay, now next topic. The fourth point, which is in case when the surface is revolved around. Okay, the earth is revolved around when the fourth point, this is when the area or the surface is revolved about any line other than the axis, other than the axis x and y. In that situation, now in this case, what we do here, we take, this is an arc. Okay, here it is a P point. We draw a perpendicular. Let me take, this is PN here.